Hey guys, here we share our accepted paper in CVPR 2023, Fuzzy Positive Learning for Semi-Supervised Semantic Segmentation. In this task, we want to train a segmenting model using a limited labeled dataset with pixel-level annotations and a huge unlabeled dataset without any annotation. Typically, works for semi-supervised semantic segmentation explore semantics from unlabeled data by assigning pseudo-label for unlabeled data, and then they will be used in a labeled style, but the pseudo-label is not always reliable, which may hurt the model's training process. So in this work, we propose a candidate label set to help model learn from multiple probably correct candidate labels. Conventional vanilla positive learning assigns and one hot pseudo-label for unlabeled data. Once the pseudo-label is wrong, this sample will introduce incorrect gradient information and thus misguide the training. We propose the so-called fuzzy positive learning, allowing the model to exploit correct gradient from a small fuzzy positive label set. Once the class of ground truth is included in this set, the model will benefit from this sample. But there are still two pending issues. The first one is how to provide an adaptive number of labels for each pixel. And the second is how to exploit the possible ground truth semantics from multiple fuzzy labels. Our fuzzy positive learning is realized in a plug-and-play manner, and this is the pipeline of whole method. The original and disturbed unlabeled image will be fed into the model respectively as usual. The critical difference is we designed the fuzzy positive assignment module to generate fuzzy positive label sets for each pixel to guide the training process through the fuzzy positive regularization. For each pixel, fuzzy positive assignment generates k candidate labels adaptively. First, the output of models will be normalized as probability, and a hyperparameter named upper probability threshold t will be set, for example as 0.9 or 0.95. Then we will sort all probability values in a descending order and calculate the cumulative probability sequentially. We will record the first n value where the cumulative probability greater than tu. Finally, the k will be set as the larger one between n-1 and 1. The optimization objective of fuzzy positive regularization is encouraging the model to increase the output of all classes in the fuzzy positive label set. It can be formulated as this equation, and can be further mathematically approximated as this equation, which is our loss function for unlabeled data. We test the effectiveness of fuzzy positive learning on two datasets, Cityscapes and Pascal-Voc, to the E2. It can be shown that fuzzy positive learning boosts the performance of 3 baselines on all settings. We further define the positive gradient score to help us analyze when and why fuzzy positive learning works. It is defined as the ratio of ideal gradient to the practical gradient, which is calculated by unsupervised loss with ground truth and output of model, respectively. In the case 1, the pseudo-label is correct, that is, the GT is the top one predicted category. In this case, both of the score calculated by vanilla method and our method is positive, and our score is slightly smaller than vanilla score. In the case 2, the top one prediction is wrong, but the ground truth is in the categories with top k probabilities. In this case, the score calculated by vanilla method will be negative while our score is still positive. In fact, this is where the superiority of our method comes from. In the case 3, the pseudo-label is wrong, and the ground truth is also outside the fuzzy positive labels. In this case, both scores are negative, thus neither method is better or worse. In Figure A, there are some samples of positive gradient score. It can be seen from the figures that our method enjoys a much larger region with positive score, which will benefit the training process. And in Figure B, the statistical values of positive gradient score can be able to explain the superiority of our method in case 2 more intuitively. Thank you for your attention to our work. The code for this work is open sourced at this link. If you come up with any question, welcome to contact us.